Welcome to our video on a summary of factoring techniques. Basically, the only objective we want to discuss here is how we can kind of summarize all the different ways we can factor most things, right? Some things are so specialized that they need special tools, but for the most part, the vast majority of the things you're going to come across in a typical algebra or pre-calculus type of class can be factored with just a small number of tools. The first thing you always want to check, no matter what kind of stuff you're faced with, and this one looks pretty complicated, right? Bunch of letters and bunch of numbers and powers, and it's just all over the place. Well, the first thing you always want to try is there a common factor I can take out of everything, right? Because if you can factor something out of everything, what you're going to be left with is always going to be simpler. And that's the whole point of math, is make it simple by making it simpler, and then you can solve for the simpler version. And so you'll notice that all of them have x's. Well, sorry, not all of them have x's. All of them have y's, though, and then all of them have z's. And in fact, you've got a y squared, y squared, y squared, a z cubed, z cubed, z cubed. Fantastic. I'm going to take that out of all three pieces. So we factor out the y squared and the z cubed, and what's left is just the x squared, the 7x, and the 6, and you go, hey, that's a quadratic. I know how to factor a quadratic. I can factor that really easily because I know since there's just a 1 in front of my x squared, then if it's going to factor, I have to look for two factors of 6 that are going to add to 7. I know they have to add because these are both positive, right? And I go, oh, well, 6 times 1 gives me 7. So of course, you factor it as x plus 6 and x plus 1. And now that big, huge, ugly thing has factored into three simple little pieces. Now, sure, the y squared z cubed still look complicated, but it really isn't. It's just two y's and three z's stuck together, right? So what we've learned is no matter how ugly something is, the first thing you always want to try is factoring out a greatest common factor. Now, it is good if you can to arrange your polynomial in either ascending or descending order, meaning highest power first down to lowest power or lowest power up to highest power. But when you're stuck with something like this where there's a bunch of x's and y's and z's, you might not really understand what the highest and lowest power is. So don't waste a lot of time trying to figure out number one. If you see it, great. If you don't, it doesn't matter. Go to number two always. Always try and factor something out. And even if you don't see the greatest common factor, factor out whatever you see they have in common and then check again. And if there's more you can factor out, keep doing that until you've pulled all of the factors out that you can, until you've basically found that greatest common factor. Now, once you've done that, whatever is left over, the next thing you want to check for is, well, am I left with any of my special things, right? These special things meaning we recognize there are certain things that factor a certain way. So we're going to look for the difference of two squares. Anytime you have something squared minus something squared, and stop thinking of it as just x squared minus y squared. Think of it as something squared minus something squared, because it could be something far kind of uglier than just x squared minus y squared, but it's still of that same family. So think about if you had, 4x squared minus 16. That's still something squared minus something squared, because if I take the square root of this term, remember terms are anything separated by pluses and minuses. So this term, the square root of it is 2x, and the square root of this is 4. So you can see that this is something squared minus something squared, right? So it fits that pattern. Same thing with looking for something cubed plus something cubed or something cubed minus something cubed, right? The sum of two cubes and the difference of two cubes. So you want to look for those three special things. And you know what? I'm going to throw in here one more special pattern you should look for, and that's our friend, the common quadratic, right? Anytime you see something of the form ax squared plus bx plus c, where a, b, and c are anything other than 0. right? So it could be 1, like we saw in the previous example when we had x squared plus 7x plus 6. That's a real common thing. When you recognize a quadratic, you know, okay, well, that's a quadratic. I can now factor the quadratic either kind of by guess and check or using the quadratic formula. But we should throw that in there as a fourth, very special, very common pattern to keep our eyes open for. Okay, if we don't see any of those, then we're basically left with a couple other tricks. If the expression that we're left with right after we've pulled out a common factor, or if there was no common factor to factor out, if the expression has 3 terms, then we try to factor as a trinomial, which really means just we're trying the ax squared plus bx plus c thing. If the expression has 4 or more terms, factor it by grouping. Group some things together and then see if you can pull something out of that factor. That usually only works for even power, even so 4, 6, 8, things like that. But especially, in these types of classes, you're probably not going to see anything more than 4 anyway. And then you're going to just continue doing that until everything is done. So if you had like 8 terms, you could think about putting it into 2 groups of 4 and then apply your techniques to each of those 4 groups and then see if you can combine them and things like that. But basically, the bottom line is you only have a few things to try. Try to factor out a greatest common factor, then look for a quadratic or a difference of squares, a difference of cubes, or a sum of cubes. If you don't see any of those, then if you have 4 terms or more, usually just 4, try factor by grouping. And that should really tackle just about anything you're going to see. If none of those tricks work, then you just have something that either doesn't factor or it factors using a really unique technique that you maybe haven't learned yet. Okay, so here's another example. 48 a to the 4th c cubed minus 3 b to the 4th c cubed. And you go, hey, they both have c's. In fact, they both have c cubed in them. And then, hey, this has got a 3 and 48. If I do 4 plus 8, that's 12. So I know 48 is divisible by 3. So I can take the 3 out and the c cubed out, which is right here, and then see what's left over. Well, if I divide 48 by 3, I'm left with 16. If I take the c cubed, I'm left with just a to the 4th, right? Same thing here. If I take the 3c cubed, I'm just left with b to the 4th. And look at this. Do we recognize that? That second piece is a difference of 2 squares, right? Because 16a to the 4th is a perfect square, as is b to the 4th. So remember, I told you want to be thinking of these things in generalities. So what's the square root of 16a to the 4th? Well, that's 4a squared, right? 4a squared times 4a squared would be 16a to the 4th. And then the square root of b to the 4th is b squared, b squared, b squared. So we know that anytime you have something squared minus something squared, you get their square roots separated by plus and minus. That's the simple pattern. Now you check what you have left. Well, I've got something squared and something squared, but it's a plus. And we know we can't do anything with that, right? So the sum of 2 squares is prime. That doesn't factor at all, at least not with real numbers. If you move on and learn about imaginary numbers, you'll know that this factors using imaginary numbers, but we don't have to worry about that here. But here we have another perfect square and a perfect square separated by a minus sign. So we can apply the same rule again and we go, aha, the square root of 4a squared is 2a, right? The square root of b is b. So there's square roots with a plus, there's square roots with a minus. And then you look at what you're left and you go, well, those are all just linear terms, right? It's just 2a, there's no powers. There's no powers. That's what we mean by linear terms. And so those are prime. We know that any individual linear terms are always prime. There's nothing you can factor out of a linear term other than a greatest common factor, right? Like if they both had a 2 in common or something like that. But as long as you pulled the greatest common factor out of the beginning, nothing's going to be left in any of these other terms. So that's as far as we could go. This thing is factored down as far as it'll go, and we're done. So that's just a couple simple examples of how we can kind of put all of these different factoring techniques together.